not bore you any further, we'll start with this session. Sir, you may take the mic. Thank you so much. Thank you so much for coming here. I'll pin you to the screen.
Yeah, good evening, everyone. Thanks for the introduction. So, yeah, today I will be going to speak about binary star systems. Okay, so I will try to keep it as simple as possible. Okay, so if you have any questions, you can just listen to my lecture, and at the last, we can have some questions. So, I will try to take you through the world of binary stars. I will try to introduce you to different types of binary star systems. Why are they significant? And what research we do, and why is it significant to study binary stars? Okay, so let me share my screen. I think my screen is visible, right?
Yes, sir.
Yes.
Yeah, yes. Okay, so today our topic is like eclipses, exchanges, and explosions, everything related to binary star systems. Okay, so during this talk, I will be introducing you to various concepts. Maybe some of the concepts will be very new to you. Don't worry. If you have any questions, we can interact at the last. Any concepts, if you don't understand, you can just let me know. You can raise your hand. So I will try to make it even more simpler. So now let us start our session. So before jumping into binary stars directly, I just want you to introduce you to light and astronomy. Why light is so important for astronomers? So if you speak about astronomy, light is a very, very key component to us. Okay. So whatever the light we receive from different celestial objects, we try to understand that object through light. So we analyze the collected light, okay, which is collected basically using a telescope and a detector. It will give us a lot of information about the celestial object, like the temperature, its chemical composition. And not just that, it also tells us about the distance and the motion of celestial bodies also. It is such an important component for us in astronomy. Similarly, we make use of this light from the stars and we try to understand how it plays a key role to us. And now coming to the binary star systems, I want to give a clear distinction between optical pair and or optical binaries and the gravitationally bound binary star systems. So whenever you look from the Earth frame of reference, so all the stars appear to be on the celestial sphere, like just side by side. Okay, though they are very far from each other, they all appear to be just side by side, right? So here, if you can see such an example, here there are two stars, A and B. So for any viewer, though those two stars are like very far, pretty far from each other, okay. So from the on the sky plane, they appear to be just side by side. Such a binaries, I mean, such stars are called as optical pair. They are not gravitationally bound to one another. But what I am going to speak today is about gravitationally bound binary systems. Okay, so to have a clear distinction, I'm differentiating optical pair from that of the binary system. Now coming to binary star systems, what are these exactly? So if you look at this beautiful graphic, you can see two stars are orbiting around one another. Okay, so they are orbiting around the common center of mass and they are gravitationally bound to one another. Okay, they have their own orbits. And whenever they complete one rotation, we call it as rotational period. Okay, all this information can be obtained from the light curve, something called as light curve of the binary star. I will discuss about it very soon. Now let us explore more. So among these two stars, like you have seen earlier, the brightest one is called the primary star and the lesser brighter one is called the secondary. Okay. And binary is the keyword coined by Sir William Herschel. You might have heard of William Herschel. He is a very prominent astronomer. In 1802, he coined this word binary. And as I mentioned, so they are gravitationally bound to one another and they orbit around each other. So they obey Kepler's laws of planetary motion. So making use of Kepler's laws, we try to understand the orbits and various parameters related to the binary star system, especially orbital parameters. Now, what do we do exactly making use of binary stars? So one is the photometry and spectroscopy, especially. So photometry is studying about light, okay? Studying light. And spectroscopy is also the same, but we try to understand its chemical composition, its temperature, and all other its motion, basically something called as radial motion from the spectroscopy. So these two studies help us, these two studies provide us with very, very, very good insights related to that of binary system. And whatever the light we receive, we try to plot that light on a graph, simple graph, time versus brightness or time versus flux. We call it as light curve, and this light curve provides us very valuable insights. I will be discussing about this in detail very soon. Okay. Now, why binary stars? Okay, there are so many binary stars in the sky. Yes, there are. How many? More than two-thirds of these stars, whatever you see in the night sky, are part of binary or multiple star systems. They are extremely important. Why they are important? One is to measure the masses of the stars. Since they obey Kepler's laws of planetary motion, so these systems help us to measure the masses of the stars very precisely. And not just that, they also provide valuable insights into effects of stellar companionship, like how these stars might have formed and why they have formed in a group. Like sometimes you see two stars in a system, sometimes three, sometimes four. So it is very important to understand how these systems might have formed. And also the planetary systems. So sometimes binaries are found to be not just alone. So there will be planets around these systems or some substellar objects around these systems. So it is very important to study those. Now, as I mentioned just now, so it is very crucial to understand how these systems might have formed, and not just about the formation. It is also important to understand how they evolve, how they influence each other's evolution, and over a period of time, what happens to them. Do they sustain as a binary system forever? Or over a period of time, something happens to that? I mean, something happens to those systems. That is very crucial. So in order to understand this, so astronomers try to study different types of binary systems, and they try to test each of these binary systems with the existing models. There are various theoretical models, and we try to observe those, I mean, different types of binary systems, and we try to test them. Okay, which is very important for us. Each and every binary system we observe brings up a very new insights to us. Sometimes they pose questions to the existing models also. That is how these are like still one of the important research areas in astronomy. Now, because of the advancement, we have very good telescopes now. We have very brilliant space telescopes, whether it is TESS or whether it is Kepler, or now we have JWST. So, and we have very high resolution spectroscopy. And because of this, thanks to space telescopes, we have very precise photometry, which help us to study these binary systems with a great precision. Now, before jumping into more about binary system, I just want you to know about our neighbor star system. The nearest neighbor star system to us is Alpha Centauri system. You might have heard of this name earlier. So this system is about around roughly 4.2 to 4.4 light years away from the Earth. It has three stars primarily: Alpha Centauri A, Alpha Centauri B, and there is another star within this system called as Proxima Centauri, but it is a bit farther from these two stars. So these two stars form a binary pair, and around this binary pair orbits the Proxima Centauri. So this Proxima Centauri is our nearest star after Sun. Okay, and there is one planet known to us, that is Proxima B. This lies in its habitable zone. Okay, now after I classify the binary systems, I will let you know to which classification this binary system falls under, Alpha Centauri system falls under. Now, if you look at this is the orbit of Alpha Centauri B around the Alpha Centauri A. So here you can see, right? So this is Alpha Centauri A, and here is our Alpha Centauri B. So just for comparison, you can see how far the Alpha Centauri B is from this Alpha Centauri A, and Proxima Centauri is even more farther. It is almost 13 astronomical units away from A and B. So that farther it is. whereas Alpha Centauri b is like around or just beyond the orbit of Uranus, and here you can see for comparison. Now, different types of binary systems. So first we have something called as visual binary. So the name itself says visual. Visual means what? So you can see them directly, or they can be observed directly, making use of a telescope. And then we have spectroscopic binaries. So spectroscopic binaries cannot be resolved using a telescope directly, like that of visual binary. They are very, very close to one another. And these binaries can be analyzed, or these binaries can be detected and analyzed only through spectrum. Okay, basically from the variation in the spectral lines. Next, we have astrometric binary system. This type of binary system, again, uh, is very important because the presence of the secondary star can be detected only through the wobble, or like say only through the variation, tiny variations in the primary star's position. I will be explaining it with an example very soon. Then the last but very important category, eclipsing binary system. The name itself says eclipsing. You know about solar eclipse and lunar eclipse, right? Similarly, whenever you look at this star system, whenever two stars orbit around each other, and whenever they eclipse each other, okay, so there will be a clear fall and rise in their brightness because of these eclipses. So that is the reason we call them as eclipsing binaries. And generally, I work on eclipsing binary systems, which I will be explaining in detail very soon. Now let us explore each of these binaries. Now coming to visual binaries, just now I have told you, making use of a small telescope or a telescope, you can just simply resolve them as two different stars, two distinct stars. So such a binary star system is called as visual binaries. And the example I have shown earlier, our neighbor, Alpha Centauri and Alpha Centauri b, they fall under this category. Okay, so basically, they are visual binaries. They have a separation of about 14 arc second. So they are visual binary. So with a telescope, you can clearly see that these two stars are well separated. Now coming to spectroscopic binaries, as I mentioned, these cannot be resolved using a telescope because one of the component could be like very small, or one of the component is pretty close to the other component. In such a case, using a telescope, it is very hard for us to see them to be two different stars. Now, in such a case, what you have to do? In such a case, we rely on spectrum of those stars. Okay, so now again, these spectroscopic binaries are classified into two types: single line spectroscopic binaries, where variation in one of the spectral lines uh, or variation happens only on one set of lines. And then we have double line spectroscopic binaries, where the variation uh, is from both the components. One of such example is Mizar in Ursa Majoris. I think you know Mizar. Mizar is also one of good examples for this. Now, let me show you with example. So here you can see there are two stars. We have nomenclated them as A and B. So whenever they orbit around each other, so one of the star appears to move towards you, whereas the other one appears to move away from you. Similarly, here in the third case, you can see B is appearing to move towards you, and then A appears to move away from you. So whenever they appear to move towards you and away from you, okay, then the spectral line undergoes something called as blue shift and red shift. Okay, whenever the light appears to move towards or comes towards you, it generally undergoes blue shift, means whatever the spectral line which is there, it moves towards the blue line or blue region. Whereas the light which is coming from the other star which is moving away from you, the light which comes from that star undergoes red shift, means the line will move towards, or like say it gets shifted towards it. So because of this variation in the spectral lines, where you call it as blue shift and red shift, we make use of this concept to study these type of binary star systems. And basically you get something called as radial velocity from this. And making use of radial velocities, you can determine the mass ratio of these stars. Okay, mass ratio is simply the mass of the second star to that of the first star. You will get it from this particular spectroscopy. Next, we have third category of binaries. Here, the third category is very, very interesting one. You know Sirius, right? So Sirius is Sirius is the brightest star in our night sky, but it is not alone. Sirius is accompanied with another one, a white dwarf. It is called as Sirius B. So Sirius AB system is a very good example for astrometric binary. Now, what is astrometric binary means? As I mentioned, the second one is a white dwarf. It cannot be seen directly through a telescope. Okay, but that white dwarf will cause the primary star or like say Sirius A star to wobble. You know what is wobble means, right? So it undergoes a little, it gets perturbated. Okay, its motion gets affected due to the pull of the white dwarf. They move around each other, right? So Friedrich Bessel is the first one to detect the this variation in the Sirius path, and this is how it is. So here is the path of Sirius A in the space, and then you have Sirius B. Because of the presence of Sirius B, now what is happening to the Sirius A? It is getting affected. It is not a straight line. You can see it clearly. It is undergoing a perturbation. It is getting wobble. Okay, that wobbly movement is because of the presence of a white dwarf along with Sirius A. So Sirius AB system is not a single star. It has a companion with it. It is called as Sirius B. It is a white dwarf. Now coming to eclipsing binary stars. Eclipsing binary stars are really interesting. The infographic or the graphic which I have shown you at the first is basically an eclipsing binary system. So assume that you are looking at the star system exactly like this, it means it is along our line of sight. So whenever they orbit around each other, each of these stars are eclipsing each other. Now, what is eclipse? So one star blocks the light from the other star. This is called as an eclipse. As I mentioned earlier, the bright star is called as primary, and the lesser brighter one is called as the secondary. Now, whenever the primary star is being blocked by the secondary star, that will be one eclipse. And whenever the secondary star being blocked by the primary star, you call it as the secondary eclipse. Likewise, we have two eclipses here. The primary star is being eclipsed by the secondary star. You call it as primary eclipse. And the secondary star is being eclipsed by the primary star. That is called as secondary eclipse. And because of these eclipses, now whatever the light you receive from this binary system has a very good interesting feature. We call it as light curve. I will show you how does it look. Now please look at this graphic. So here whenever two stars orbit around each other, whenever there is an eclipse, you can see that there is sudden drop in the brightness of the system. And whenever the secondary star is being eclipsed, since it is lesser brighter one, there is a small dip here. This is called as light curve. The beauty of eclipsing binary system is this. So whatever the light you receive from this star or system, okay, because of these eclipses, there is a sudden fall and then rise in the brightness of this system. That is because of happening and leaving of the eclipse. This is exactly during eclipse. This is exactly the minimum where the eclipse is happening. So likewise, you have primary eclipse where the primary star is being eclipsed, and this is called as secondary eclipse where the secondary star is being eclipsed by the primary one. Now, how this is helpful for astronomers, we will see. Before going to how it is helpful, so the eclipsing binary stars are again classified into three types based on how they evolve and all. So here you can see the first one, there are two stars which are perfectly very good. They are like exact spheres and they are well separated. There is a clear separation between them. So such type of binaries are called as detached binaries. Then you have one more system where one of the star is evolved. Okay, it is like bulged. Okay, and it is not just bulb. If you can see that it is looking like a squeezed one. It is not a perfect sphere, right? So you can clearly see that. It means what? After it got evolved, it is now ready to transfer its mass to the other one. Such a binary system is called a semi-detached. So mass is being transferred from this star to the other star. Now, third one, you have something called as contact binary system. Now, in the contact binary system, you can clearly see that there are two stars and there is a common envelope around them. So they are physically in contact with one another through a common envelope around them. So based on what type of eclipsing binary it is, it light curve changes or it light curve depends. Let's see some examples. So the first one is called as it is a typical example for a detached binary system where you can see a beautiful variation in the light. So here you can see very sharp minima. So this sharp minima indicates that the components are well separated. So that is how astronomers classify them as detached binaries. This is one way. Usually you can look at the light curves and you can classify them. So looking at the first one, you can easily tell that the components are well separated. So you have a flat maxima where the brightness is maximum. Then you have a sudden sharp fall. Again rise, again fall. So this is an example for detached binary system. Then we have semi-detached binary system. So semi-detached binary system में, as I mentioned, one of the star is evolved. It has increased in its size and it is ready to transfer its mass to the other one. Because of that, you can see a wavy kind of feature here. So this is semi-detached system. But though it is semi-detached system, still you can see there is a huge variation in the primary minimum and secondary minimum eclipses. And coming to the third one, as I mentioned, contact binary systems have a common envelope around them. So these two stars are almost similar. Okay, so the temperature variation will be very less in this case. Whereas in the first and second case, the temperature difference can be huge, where one of the star is very hot star, whereas the second star will be very cool star. Okay, and here in this case, you can clearly see that the components are like the temperature difference is very less. Okay, and they are comparative. Okay, so that is the reason you have a very good light curve in this case, almost like a sinusoidal wave. Now, what do we get from the light curve of an eclipsing binary system? The first thing first, whenever you get the light curve, generally astronomers don't simply observe them. Okay, we get a lot of information from the light, whatever we receive. Okay, so here if you see, so the first parameter you can easily get or you can easily deduce is orbital period. Now, what is orbital period? Whatever the time the stars take to orbit around each other. Okay, that is common center of mass. So this is very important because the shape and duration of the this affects the shape and duration of the light curve, which is extremely important. In the previous case, you can clearly see that. Okay, so the shapes are very important, and the duration for which these eclipses, or like say they orbit around each other, is also very important. Now here you can see. So orbital period is very important. We get orbital period from the from observing the light curves. Then the inclination. Now what is inclination? So it tells us about the orbital plane of the binary system. So if they are eclipsing along our line of sight, the inclination will be maximum, that is 90 degrees. Then you get totality, something called as totality, or they are totally eclipsing. Means each of the stars try to obstruct the light completely, like totally. So in such a case, the inclination will be 90 degrees. I will show you one simulation so that you will understand it very well. So higher the inclination, better the results are. I mean, whatever the parameters you deduce, they are more reliable. Now, if they are not along our line of sight, let's say they are, I will show you anyways in the simulation. If they are not along our line of sight, if they are a bit offset, in such a case, what happens is the inclination decreases. it becomes 70, or in some cases it goes as low as 60, 50 also. In such a case, whatever the parameters we deduce, they become less reliable. Okay. In such a case, you have to go for spectroscopy also. Next important parameter is mass ratio. Once we get the light curve, we make use of different models and we will try to fit the light curve using particular models. And from once you fit it, you will get an important parameter called as mass ratio. As I mentioned earlier, mass ratio is the mass of the secondary star to that of the primary star. Okay, so this is very important to deduce other parameters. Now the sizes, yes, from the light curve, you can try to understand the sizes of the stars also. I will explain it very soon. Then temperature also. So generally temperature is deduced from the spectrum of the system. And also you can deduce it's from the colors, from the light also. So whenever you collect the light of that star system from using two different filters, like say B or I or J or H. So making use of different filters, astronomers will collect light from the system and and depending on the difference in their magnitudes, they try to estimate the temperatures. So temperature can be estimated using colors and temperature can be determined using spectrum also. And not just these, okay, not just these, you can also deduce stellar masses, stellar luminosities of each of the components, and also you will understand what is happening on those stars, whether those star systems have any spots like that of sunspots, or are there any like other additional components within that system. So the eclipsing binary system gives you vast amount of information. They are like really helpful for astronomers in understanding the formation, evolution, and also the death of the stars. Now, let us explore a simulator. So I have chosen this simulator so that you will understand it very well. So let us explore it. So whatever the questions you have, I will try to answer them very soon. So this is one of the simulators generally I use for my outreach uh, to explain about the eclipsing binary systems. So I suggest all the audience to make use of this simulator, explore it, and try to play with all the available options here, the parameters here, so that you will understand how the light curve will change. So here you have the perspective from Earth, how you see the binary from Earth. And on the right side, top right, may you have the light curve of the binary system. And here you have different presets. So here you have different examples. You can choose one of these examples. Like say I'm choosing example 6. And then here you have masses, the mass of the primary star, the first star, then second star, the sizes, temperatures, and the separation between the two stars. And on the left side, you have inclination. So as I said, this is along our line of sight. If you change the inclination, you can see how the perspective is changing. I said that whenever the inclination decreases, the reliability of parameters also decreases because of this reason only. If you look at this, since the inclination is not 90 degrees, so during eclipses, okay, so the light, whatever you receive, okay, whatever the light you receive is actually from both the stars. Whenever it is 90 degrees, then only total eclipse happens. Means each of these stars will block, uh, the total light from the other component. If it is not 90 degrees, if it is any other angle, so what happens? It will be partially eclipsing. This is called as partial eclipse. Means what? Each of the stars are partially blocking each other. In such a case, whatever the parameters we deduce may not be reliable. That is the reason astronomers sometimes go for spectroscopy whenever the inclination is not 90 degrees or whenever they are not totally eclipsing binary systems. Now let us put it to be 90 degrees, and this is how the light curve looks. Because here the masses, whatever you see. So one of them is two solar masses, the other one is one solar masses. Now let us play with this. Now I will decrease the separation. So whenever you decrease the separation and whenever you make it a circular orbit. Now I have made it as a circular orbit. Now you can see how beautiful the light curve is. So whenever the eclipse is happening, there is a dip or there is a fall in the brightness. And whenever it is leaving the eclipse, there is a rise in the brightness again. Okay, now let us try to change the sizes also. Now I am changing size of one of the stars and increase its mass drastically. And let us decrease its size, or let's say something like this. Yeah. Now let us decrease the temperature also, and let us increase the temperature of the primary star. Now you can see. So I said totality, right? So this is how totality looks. So whenever it is totally blocking each other, so there you can see a flat minima. So whenever you see light curves with flat minima, the parameters, whatever you deduce from such a system, are reliable. So though you don't get spectroscopy, you can proceed with the parameters you deduce from the photometry. That is the light curve modeling, basically. So likewise, making use of this tool, you can change inclination and you can see how the light curve is changing. See, you can see clearly how the light curve is changing. So the reliability of parameters depends on how these two stars are inclined. I mean, the eclipsing system ka orbital plane is inclined with us. Accordingly, the reliability of parameters depend. And depending on their sizes also, the nature of the light curve changes. Here you can see again. Okay, let me put it back to a normal star, like say something which is twice that of the sun. And let us take the other star to be less massive and of lesser size. And the separation, unfortunately, here I think the separation is cannot be made even smaller. I don't know. No, it's the least. So, but the separation will be even more less actually in some cases. So here you can see. So if you want to categorize this, you can categorize this to be a closed binary system. Okay, that too you can put it under contact binary. And if you want a detached binary system, so I will show you one of such examples. So yeah, here it is. This is one example for detached binary system where two stars are clearly well separated. And here now they are in a circular orbit. Okay. And here you can play with the masses also. You can increase the mass of the primary star and accordingly you can change the temperature. So here I am increasing the temperature of the primary star. Right. Accordingly, you see the light curve. So I will try to share this link with you. Need not worry. So, or you can just go to internet and you can just type Eclipsing binary simulator. You will get it. Okay. So here is the resource. So it is NAAP Labs. Okay. You can just search for it and you can play with this simulation in your free time. So, and here there is something called as HR diagram. I don't know how many of you have heard of HR diagram earlier. HR diagram is something called as Hertzsprung-Russell diagram. This is very important tool for astronomers because here we plot temperature versus luminosity. Okay, and it will show you whether the stars are still under hydrogen burning stage or they have completed their hydrogen burning. Accordingly, they will slowly shift. So now I will show you. See here. Can you see how the second star got shifted from the main strip? So whatever the line you are seeing here, this indicates that still these stars are burning hydrogen. Now, whenever I try to increase the size of one of these stars, that star is leaving that strip. It indicates that it is evolved. This is a semi-detached system. Okay, so depending on whether a star is still under hydrogen burning or it is evolved. Okay, so we can decide or we can try to understand what happens to it later. This is very important tool for astronomers. Okay, if you have never heard of HR diagram earlier, if you are interested or if you are passionate about observational astronomy, I recommend you to explore HR diagram also. So it plays a very key role in understanding the nature of the stars, their evolution, and what happens to a star once hydrogen burning is done. Okay, so please explore it. And also, whenever you get some time, please explore this tool also. This is a free tool which is available on internet. Now, why astronomers have to study binary systems? I have already mentioned some of the significant, you can call it as significant, some of the points I have mentioned earlier. Now, why I study eclipsing binary systems? Because eclipses you already understood. Now, let us focus on exchanges. Now, what is exchanged between these two stars? They exchange mass, they exchange energy. Okay. Because of that, the temperature keeps on changing. Whenever they transfer mass, accordingly, their angular momentum gets changed, their period changes. It is a very beautiful thing to explore. Okay, so here you can look at this simulation. Here you have two systems. These can be treated as like eclipsing systems, assuming they are along our line of sight. So over a period of time, what happens is one of these star, because of the mass variation, it evolves, and once it evolves, it will transfer its mass to the secondary star, to the other star. You can say it as other star. This is called as mass exchange, or you can call it as mass transfer. So whenever it transfers its mass, so now what happens slowly, the angular momentum changes. Slowly these two systems over a period of time come closer and they now become marginal contact configuration. See, this is only one possibility I'm explaining. Not all systems will follow this trend. I have chosen that particular system which undergoes this cycle. But don't think that all systems, all eclipsing binary systems will follow this trend. Please remember, this is one of the models. That's it. Don't think that this is the only model. Okay. I have chosen one of such models to explain you what happens to a binary star system. So whenever the mass transfer happens continuously over a period of time, they come closer because of change in angular momentum. And over a period of time, they go even more closer and closer, and they become deep contact stars or deep contact binary system. And if this still happens, if they continuously lose angular momentum even now, and one day they end up as a blue straggler. Blue straggler means what? One of the star engulfs the other star. They merge into a single star. How beautiful it is. Now, why we are calling it as a blue straggler? Straggler, why we are calling it as a blue straggler? Because as I have shown you HR diagram, each and every star has its own place on HR diagram. But there are some very, what I can call them uh, as I cannot call them as like some different object, but there are some objects or some stars like blue stragglers which have excessive brightness compared to that of their masses. This is a very interesting part because each and every star, depending on its mass, has its own temperature and brightness. But these blue stragglers are exactly like different from the regular stars. They have extreme luminosity for their masses, given masses. Though their mass is little, but they are very hot and very bright. That is the reason these are put at the top of the HR diagram. Their place will be at the top of the HR diagram. They are extremely hot and bright. So, in order to understand their origin, or in order to understand how blue stragglers form, this is one of the possible ways. So, eclipsing binaries, to be specific, contact binaries are known to be progenitors for blue stragglers. Is this true? Have anyone seen me? Yet, astronomers are exploring this way. But if you study deep contact binary stars, so there are high chances that these systems could be progenitors for blue stragglers. Over a period of time, they lose angular momentum continuously and they merge one day, forming blue stragglers. That this in graphic, whatever is there, this also shows a similar feature. So here there are two stars, like you can say solar type stars. Over a period of time, one of them is evolved and transfers its mass, and slowly they come in contact with each other. They merge into a single star. And don't forget, whatever the simulation I am showing you here, this does not happen in a single day. This whole thing will take millions and billions of years. Please remember, the life cycle of stars is not just few days. Depending on their mass, depending on how gravitationally they are bound, how tidally they are affecting each other. Okay, their life cycle goes from millions of, tens of millions of years to billions of years. Please remember this thing. It does not happen in a single day. That is the reason we study so many examples, so many stars to understand their evolution. Theoretically, we have different models. Theoretically, we have so many models which explain what might happen to these stars. But as an observational astronomer, I try to search for the solution. I mean, I try to search for those systems which will follow these models or which will go against these models. Now you may ask me, are there any stars which go against the existing models? Means yes, there are so many binary systems which pose serious questions to existing models. So whatever the existing models we have now, they have to be refined according to the latest observations. So whatever the advancement we have, we have now so many powerful telescopes, so many powerful techniques. So accordingly, we have to refine our existing models. How beautiful it is. Now there is another possibility. Here you can, and please remember, this is not to scale. This is just for our understanding. This is just an infographic. So here you have two stars. This is called the primary star, which is bright one, and the secondary star, and this is also massive one. So over a period of time, what happens? This massive star will evolve into a red giant, and ultimately it will become a white dwarf. And once it become a white dwarf, what does it do? Whatever the secondary star which is there, it will try to hinder the evolution of the second star. So over a period of time, this also evolves into a red giant, and slowly it will try to capture the mass from this evolved second star, and it will try to collect as much as possible, as much mass as possible from the other star, and over a period of time, they will end up in a supernova. You know what is a supernova, right? So this is one of the possibilities. But whatever the research I do, so I generally focus on these systems. I will try to understand what happens to these systems. Will they exactly end up as blue stragglers, or will they end up in this cycle forever? So what is that cycle? Sometimes these stars will come close. Again, they go back to this stage. Again, they become semi-detached. Again they become contact. Again, they get separated. So they keep on moving from one phase to other phase over a period of time. They may undergo thousands of cycles like that. Okay, so my job is to study these systems, but with a additional body, with an additional body. So I generally my research focuses on eclipsing binaries or closed binaries with additional components. I just want you to give a small gist about my research. So, as I mentioned earlier, so whatever the light we collect from a telescope and the detector, making use of that light, we try to deduce different parameters. We have different models, making use of modeling tools and models. We try to understand the nature of that binary. So here I'm just showing you two examples. So what all parameters we get? So we get mass ratio. Mass ratio is what? Mass of the secondary star to that of the primary star. And along with that, you will get secondary star temperature, and then you have inclination. Here you can see inclination. This is close to 90 degrees, whereas this is close to 60 degrees. So what are the parameters I have deduced here? These are less reliable for this component. Whereas for this component, yes, they are more reliable because the inclination is 85 degrees. They are almost totally eclipsing each other. So making use of these parameters, I will deduce masses of each of these stars, their radius, their luminosity, whatnot. And I will try to understand their evolution also. So here is the light curve of those two stars. Here we have made use of the data from the TESS satellite. Okay, we have collected light from the TESS satellite. TESS is a space telescope. I should call it space telescope, not satellite. So TESS space telescope, and whatever the data we got, so I have modeled it, making use of something called as WD. So WD is Wilson Devine. It is one of the modeling packages we have. We make use of it to model such light curves. And to our surprise, as I mentioned, so we also get to know their ongoing activity. So can anyone recognize what is this? These are called as flares. So we have detected many flares on these binaries. Okay, and in our research paper, so we have estimated their energies also, and we have also mentioned how many flares have been detected on each of these binaries. So we have modeled these flares also, and we have estimated their energies here. So you can see that here. Next, why spectroscopy is important? As I mentioned, spectroscopy helps us to understand the chemical composition of stars in the case of binaries, and it helps us to determine the temperature of the primary star, and it also helps us to uh, understand their motion, and making use of the radial velocities, we can determine mass ratios to be precise. So whatever the mass ratio you get it using spectroscopy is very reliable. And along with that, the spectroscopy also helps us to understand what is happening on those stars. So stars are again classified into different types based on their temperatures. So cool stars are known to be very active. They are magnetically very, very active. So they have flares, they have very big spots. Okay, so they continuously throw off matter into space. Okay, so they are known to have very, very, very keen and very high magnetic activity. So whenever you get the spectrum from those stars, so you can understand what is exactly happening in the star's atmosphere, whether they have any spots, whether they are undergoing any prominences or flares. Accordingly, you will get to know. So spectroscopy plays a key role in understanding the ongoing magnetic activity on those stars, which is very beautiful actually. And here you can see one sample spectrum. So this sample spectrum is taken from LAMOST, so which is a Chinese-based uh, telescope. So basically, we have collected it using that. And here is our observation. So this is the spectrum we got. One second. Yeah. So this is the one we got it from Lamos, I guess. This is the one we have observed. And making use of these spectral lines. Remember, light, whatever the light you receive from the stars, it carries information, especially called as spectral signatures. Whenever you get the spectrum of star, you will get to know what all elements are present in that star. And depending on how these elements are, like at what level they have, you will get to know what exactly is happening to that star. Please remember that. It is very, very important. Okay. And as I mentioned, I also focus on additional bodies. I mean to say, not just binary system. I also focus on the additional component which is orbiting around this binary system. In order to detect such systems or such third bodies, we make use of something called as period variation studies. So these third bodies, what they do is they affect the motion of these two stars. So they affect the period of the two stars over a period of time. So this can be understood from period variation. So here you can see. So this is one such a beautiful example. So this is, I think, BX3, where we have detected a third body of mass 73 Jupiter masses. And this is another example where we have found or detected 0.51 solar masses ka third body around that system. So these third bodies also play a very crucial role. They generally remove angular momentum from the central system, and they either push them towards more deeper and deeper contact stages, or they remove angular momentum, or they stabilize the angular momentum, and they make them more stable also. So third bodies are also very crucial in playing with the life of the, or you can say how the evolution of the central binary system. So that is the reason we also study the third bodies. Yeah, this is more of research. Yeah, I think I will end my session here. If you have any questions related to the basics of binary or any binary star systems or like types of binary star systems, we can have a discussion.
Okay. All right. Thank you, everybody. Thank you so much, sir. We'll take the questions now.
Yeah, sure.
Anybody who has any questions, you may raise your hand and we'll take your questions like we did the last time. Okay, a bunch of people have raised their hands. Some people have Tejaswi. Yes, you can open your mic. Let me switch on the settings to open your mic. And yes, start with the questions. Okay, Tejaswi, are you there? You can open your mic and start asking the question right away. Are you able to open your mic? Not able to unmute. And you've turned on.
Hello.
Yeah, I can hear you.
Yes, Professor. Thank you so much. This is very informative. I just want to ask that how magnitude, like absolute magnitude, play a role, or when we talk about the bolometric magnitude, play a role in this first. And the second question is like how the Roche law is acting here. And
Hmm.
the one is like the image you show for the how they detach and semi-detach. So for
Yes.
here we have considered the two same mass. So is it every time will be possible that the Roche law which we the loop like infinite loop we
Yeah,
show
understood. Yes.
the same, or sometime it will primary will be bigger or small?
Yeah. Yes. Yeah. Thank you for the question. So, first, let me answer your question related to this social laws. One thing is, depending on the here, whatever the masses of the systems we take, generally they need not be same first of all, and then especially the temperature variation. Depending on the temperature variation, actually, primary and secondary eclipses depend. So each and every binary system has its own light curve depending on their masses and temperatures, basically. So not always the two stars will have similar masses. Okay, most of the time contact binaries may you can see comparable masses, but that is also not true always because sometimes their mass ratios go very extremely low, where they are like very close to one another and they are good progenitors of um, blue starlets, like I have mentioned earlier. So coming to masses, yes, they need not be always same. Coming to temperatures, they need not be always same. Sometimes the temperature variation will be so huge. So the temperature difference between the primary and secondary will be so much different. Like say thousands of Kelvin difference would be there. And coming to the first question, like you have asked about the magnitudes, see, magnitudes play a key role, obviously. So generally what we do is we try to observe these binaries in different filters. Okay, B, V, R, I, like say, I mean to say like blue filter use करके, then red filter, then infrared also. We have infrared also. Depending on the temperature, accordingly, the magnitude variation depends. Okay. So that is the reason what we do is we uh, try to do delta mag. Depending on that, we try to understand the nature of the system, first thing. And I don't know why you have asked related to absolute magnitudes. What is your question exactly related to absolute magnitude?
So there will be the always the confusion. So that's why,
Okay.
yeah, ask that how this
Okay,
all.
got it. Yeah.
Yeah.
Yeah, I understood. So generally, absolute magnitude is different. You see, absolute magnitude, what astronomers do is we try to keep all the stars at a particular distance and we try to compare them and generally measure the magnitudes. Okay. But whatever the magnitude you receive from a star is apparent magnitude. Okay. Whatever you receive directly from the star, whatever the magnitudes you estimate is apparent magnitudes. But if you take the same star to that particular constant distance, that is 10 parsecond, and if you keep that star there, how does it look? Is the absolute magnitude. Making use of this apparent magnitude and absolute magnitude, astronomers will estimate the distances basically. Okay. So yeah, hope I have answered your question. So what are the magnitudes we generally get is, yeah, apparent magnitude only. So absolute is the one. when you place the same star at a distance of 10 parsecond and measure its brightness or like the magnitude.
Okay, thank you.
Yeah.
Thank you.
I think I forgot about Roche lobes, I guess. Sorry. Yeah, she asked about Roche lobes. It's a very good question. Roche lobe is, yes, it looks like an infinite symbol around these two stars. So whenever a star evolves, it will try to fill out its Roche lobe. Roche lobe is the region. It's a potential till where the mass will be bound to that star. One star evolves. Once it crosses its Roche limit, it cannot hold that mass with it. So then slowly it will transfer that mass to the other star. In the case of contact binaries, that Roche lobe is around both the stars. They share a common envelope around them. So whatever the mass exchange will happen, that will happen between those two stars only. Yeah,
So that's why we mentioned the Lagrangian point L1.
exactly. Yes, exactly.
Okay, thank you.
That will help us to understand how the mass is being transferred from the evolved star to the other star.
Okay,
These Lagrange points are also important. Yes, L1, L2, L3. Yeah,
okay, thank you.
yeah.
Thank you, Tejasvi, for your question. Next, we'll have Sripad. Sripad, you may go ahead and unmute yourself and ask the question.
Hi, sir. My name is Reepat.
Yeah, hello. Yeah,
Thank you
hello.
for the awesome session. I have I have a few doubts, but I'm going to ask two of them. Um,
Yeah,
one is Sirius. The star Sirius has a white dwarf orbiting it. No, so
yes,
is it affected by the white dwarf? Like you told, white dwarfs can take material from the other star. No, so is
yes.
first question is Sirius affected by that? And the second question is, how do we differentiate the light curves of exoplanets and binary stars?
Right. Very good. I really like your question, actually. Yes. So whenever there are white dwarfs, generally what happens is they are like they're basically called as compact objects. Okay. So they are very massive, though their size is like very less. They are very massive, and generally what they do is they will try to um, over a period of time, they try to take mass from the other star. Okay, but here, see, it does not. Uh, in all the cases, it does not like simply eat away the other star. Okay, so in the case of Sirius B, okay, so Sirius B is a very massive white dwarf. That is true. I think it is a pretty far from the Sirius A. Okay, the distance between them is like pretty far. And till now, we did not find any evidence for the strong mass transfer or violent disruptions happening between those two stars because they are very well separated from each other. Okay, one thing. Though it is like tidally locked, and I mean, though they are like tidally affecting each other, they're gravitationally bound, but still we did not find any like strong mass exchange or mass transfer happening or any violent disruptions happening as of now. But in some other binary systems, like I have shown in the other case, if they are like very close to one another, in such a case, once the other star starts evolving, it will receive the mass from the other star. Okay, and over a period of time, they come closer and closer, and they undergo a massive explosion. Okay, so in the case of Sirius A and B, as of now, okay, as of now, there is no strong mass transfer or violent disruptions happening. They are very well separated, and I think the orbital period is also over 50 years, I guess. Okay, so maybe over a period of time they may come closer, and maybe its fate will be different. But as of now, yes. But there are other binaries where you have compact objects where they undergo violent explosions. And in some other cases, if the two stars are very massive, each of them end up as compact objects, and over a period of time, they merge together and they give out gravitational waves also. Like neutron mergers are there, black hole mergers are there. I think some of you have questioned about black hole binaries also. Yes, there are black hole binaries also. Over a period of time, if they merge together, they will give out like gravitational waves. But anyways, my research area is not into that extent. So I generally focus on main sequence stars, that is like hydrogen burning happening stars. Yes. So there are some binaries where you see compact objects which take away mass from the other star where they undergo violent explosions. There are some systems which are still stable also, like in the
So,
case of Sirius A and B.
so also, how do we separate the light curves of binary and exoplanets?
That is also a very good question. Like I have said, these binary star systems, if you take example of eclipsing binary stars, they have a periodic light curves, right? The primary and secondary and primary are again like very good. Like the period is like very good. I mean to say it is periodic. You know the period of the binary already. Let us assume there is any third body, like say any additional component around it. If it is bright enough to affect the light curve of this binary system, then you can simply make use of mathematical functions where you can make the eclipsing binary as a flat, removing the binary effect. There you can detect the third body, or let's say it can be a massive exoplanet or a brighter object. Okay. So, but in the case of single stars, it is very easy. You have something called as transit method where you can clearly see the transit of the exoplanet and you can detect it. But in the case of binaries, it is not that easy because I generally work on binaries with additional bodies, right? So it is very rare where you can see a clear signature of a third body's light in the eclipsing binary system. But we find third light. We detect third light also. If you see in this case, I think I have mentioned it somewhere. Where is that? I just want to show you that. Okay, I don't know whether I have kept it or not. But in some cases, you detect third light also. I don't think I have kept it here. Yeah, in some cases, you detect third light also. But it won't be directly like where you can directly subtract it. But in some cases, you can do that. If the third star is comparable in mass and comparable in its brightness also. In such a case, yes, you can do that. You can simply subtract or you can simply eliminate the binarity and the remaining light curve gives you the signature of the third light. There are many mathematical tools which generally do this. We generally run such pipelines.
Thank you, sir.
Yeah.
Thank you for your question. Let's take a Tufa's question. Tufa, you've raised your hand. You can unmute your mic and start the question. Are you there? Tufa, Bora.
No, you are not audible like this. I think your voice is very feeble.
Yeah, then you might be unmuted. You're not unmuted. You speak.
Yeah. Now you can ask your question, I guess.
I think
But if you are facing any issue with your mic or something, you can just type that question in in our comment section.
yeah. You can write your question in the chat, Tufa. I think you're
Yeah,
not.
chat or something. Yeah, yes.
Okay. I think
I think we
Tufa.
have some questions from the comment section. I mean, chat also, I guess.
Yeah, you can take Onkar's Nath's question. In
Okay.
spectroscopy of stars, when we observe the light from particular star, how do we ensure that how do we ensure the spectrum we record actually belongs to that star, given that the night sky contains thousands of other stars emitting light simultaneously?
Yeah. That is really interesting question. Basically, what we do is see, we have so many powerful telescopes, and generally we don't see the whole sky. We should not forget that we generally don't look at the whole region of the sky. We specifically target each and every object. Each and every object has its own coordinates. Okay. So we will try to keep that our targeted object at the center of our field, and then we will receive or we will collect light from that object. And very good question. What if there are like other stars nearby, and what if they manipulate the information we generally get from this star. Yes, sometimes that also happens. Okay, so in such a case, there are some techniques, okay, where we try to eliminate the contamination of other stars. Okay, we will try to eradicate as much as possible. Whenever the field is very crowded with so many stars, we try to eradicate the contamination using different techniques. And though we do that, still there will be a little bit contamination. That is possible. But generally, if the field is normal with least number of stars, and if your object is very bright enough, you will get good amount of light from that object because it is targeted system. It is at the center of your field. Directly you will get the spectrum of that star. Or it is not about just spectrum or about the light curve. Generally, you will get the information from it. But in very rare cases, if the field itself is like very crowded and if there are so many bright stars nearby, then there are high chances that your light generally gets what we say contaminated or something.
So I think two first question has came in. My question
Yeah.
is, her question was about the type La Supernova, which came from explosions of binary star. I understand they originate in binary systems, and heard that I've heard that
Yeah, yeah.
their brightness can be used to calculate the distance of the galaxy. Since the
Mm-hmm.
brightness might vary depending on the star, how do astronomers ensure their supernova are reliable standard candles, and how exactly
Mm-hmm.
is the distance to the galaxy or even the universe calculated from it?
Yeah, it's also a very interesting question. See, generally, um, these whatever the supernova which happens, we should not forget that. Say, for example, if a supernova happens now, okay, so it will stay for so many weeks generally, though its brightness fades away. We should not forget that supernovae won't stay forever. So its brightness may peak for few days, like a week or something, and over a period of time they fade away. Okay, so generally the supernovae events happen here and there throughout the galaxy, and not just that, they happen in other places. I mean, other galaxies also. So you have asked, I think you have asked like how astronomers ensure that supernovae are like standard candle something, right?
Yes, reliable
Is that
standard.
the question?
Yes.
Yeah. So as I mentioned just now, these supernovae, whenever they happen, so they become very good sources to detect, I mean, to determine or to estimate the distances to the nearby galaxies most of the time. Okay, so let me take one example for you. It is not about like just type 1A supernovae. Let me pick one example to. I don't know whether you follow the supernova events like frequently or not. I think if you take example of 2013 EA, I guess, if I remember it appropriately. So depending on how much time the supernova event exists, like say for how much time or how many weeks the brightness still exists. Accordingly, during that time, we try to estimate the brightness. We try to estimate other parameters of that supernova, and then we will try to estimate the distance to the galaxy. And as you said, standard candles. I don't know whether you heard of Cepheid variables or not. Cepheid variables are generally treated as standard candles. They give you more reliable, or they stand as more reliable tools or like say objects for determining distances. Okay, so Cepheid variables are very good objects, and not just those. There are some systems uh, like uh, uh, like RR Lyrios, some systems are there. So still they are like very good sources to, or they act as a standard tools for determining distances to distant galaxies and all. So what I say is, if you have to call something as like standard candles, so I prefer Cepheid variables to be more standard candles or like say standard objects for determining the distances to distant galaxies compared to that of supernovae. But yes, Though I don't work on supernovae, but still I heard that like they are also used to estimate the distances to galaxies, uh, like whatever the galaxies they belong to. Yeah. So yeah, I don't know like much about the like how they consider these supernovae as standard candles, but to my research concern, like I consider Cepheid variables to be more appropriate candles or like say standard candles for distance estimation.
All right. Thank you, Adupa, for your question. I think Shivam has raised his hand. You may go ahead and ask the question. You can
I
unmute it.
think yeah, yeah.
Hello,
Okay.
am I audible?
Yes.
Yes, yes.
So my question was that, like we talked about the mass exchanges happening between a binary star system. Does
Yeah.
the same type of mass exchange happens in a triple star system like the Alpha Centauri AB and Proxima Centauri?
Like if you take the example of Alpha Centauri system, we should not forget that the Proxima Centauri is way too far from the central binary system, or you can say the pair, because it is almost like 13 astronomical units away, though they are gravitationally bound to each other. So the separation makes it very hard for them to directly exchange mass. Okay. If the system, I mean, if you take a triple system which is like very closely bound to each other, where the orbital period is hardly few days or hardly few hours, in such a case, there are high chances that they continuously exchange mass, and there are high chances that there are like violent incidents happening. But in the case of this type of binary systems, like especially Alpha Centauri A and B, they themselves are like very well separated. They are visual binary system. And coming to Proxima Centauri, it is even more farther from the central system. So I don't think Proxima Centauri can directly or like say it can transfer its mass to the central system. That is not possible because it is very, 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 very well separated. I think I have mentioned the orbital period also. It is, I think, over 80 years or something for it to orbit around the central system. So it is pretty far. So the mass exchange can happen if they are like very close, okay, and they are very much tidally locked, especially in the case of contact or semi-detached systems. In such a case, yes, it happens. And someone earlier asked about Roche lobe, right? So each and every star has a potential till where it can hold its own mass. But if it is evolving and if it is beyond that limit, it cannot hold its mass anymore. So it has to push out or it has to give out that mass. So then only the mass exchange happens. So evolution also plays a key role here, not just being a part of a triple system or a binary system, simply brings up this mass exchange. So evolution also plays a key role. So one of these stars should evolve and it should be ready to give out its, I mean, it should ready to exchange its, then only it will be possible.
Okay, sir. Thank you.
Thank you, Shivam, for your question.
Yeah, thank you.
We have a very interesting question from Saraswat. How do we distinguish binary systems if their plane is normal to Earth, and how do we study them?
Yeah, yeah, it's like very interesting question. I have seen that question during my talk also. As I have shown, if they are along our line of sight, then only we call them as eclipsing systems. If they are not along our line of sight, then slowly they become non-eclipsing systems. And as you said, if they are exactly normal, if the inclination is 0 degrees, in such a case, it is very hard for us to classify them as a I mean, sorry, classify them as an eclipsing system itself. So, in such a case, there will be no eclipses at all if they are exactly at 0 degrees, for example. So, if their orbital plane is normal to us, in such a case, you can't see any eclipses. So, obviously, it's not possible for us to get the light curve or to classify them or to study the variation in the brightness and all. There could be so many systems like that also. So there could be so many single stars with other component which is orbiting it in such a kind of thing, like in such a kind of orbit where its orbital plane is normal to us. That is also possible. There are such systems also. There can be also so many also. So um, To be precise, like if they are normal, yeah, you cannot classify them to be eclipsing. There are non-eclipsing binaries where the inclination is as low as 20 degrees or 30 degrees, something like that. But exactly normal, if it is 0 degrees, it is very hard to detect them or to consider them as eclipsing binaries. So you have to rely on some other techniques to study them rather than the methods I have told you.
Nice, nice. I think we'll take a couple more questions since we have a time constraint. We'll end it after a couple more questions. I think we has a question that says, "Do solar flares and CMEs affect the observational data of binary systems, and how do these affect how do these effects separate when studying data? Because due to this
Uh,
bright peak in the light curve."
Yes. Specifically speaking about solar flares, I have shown you one example where we have detected so many solar flares on eclipsing binary systems. Few of the eclipsing binary systems like this. Yes, they do affect because if you see how much variation is there in the flux. Let's take this example. This is the maximum of the binary star, but because of this flare, the maxima has gone from 3,500 to 8,500. Just 500 it has rose to 500 electrons per second because of this flare. So this is a huge energy which is like erupted from the surface of that particular binary or like one of the components of the binary system. So what we do is we try to eliminate these flaring features. Okay, making use of simple mathematical tools, we eliminate it. We take only the binary star light curve. Yeah, it's very simple to do. So, but to understand more about this ongoing activity, generally we go for spectroscopic studies, where we take the spectrum of these stars and we try to study the spectral lines of different elements, and we try to understand or correlate it with the observed flaring activity from the photometry. Yeah.
Yes, yes. I think Amoli ma'am has a question. She has a doubt. Ma'am, you can go ahead and ask the question.
Yeah. Hello, sir. This is Amoli
Hello.
from Jaipur. Uh,
Yeah.
Sir, I would like to ask you a very simple question, not very technical one.
Yeah.
Sir, we have heard about the TRAPPIST solar system, the new system
Yes.
which we have.
Trappist stars. Yes. Yes. Yes.
Yeah,
Scientist
the
one. Yes.
TRAPPIST star system. Sir, can the binary systems have something like the TRAPPIST system or some system like ours?
Yeah, that's an interesting question, ma'am. Most of the people think that exoplanets are found around only single stars. It is not true. There are some exoplanets detected around binaries also.
Okay.
Okay, there are some exoplanetary or planetary systems around binary stars. So there are exoplanets which orbit both the stars. They are called as circumbinary exoplanets. And there are some exoplanets which orbit only one of those stars. When two stars are very well separated, if exoplanet is orbiting only one of such stars, so then you have S type and P type. So there are circumbinary exoplanets where an exoplanet will be orbiting both the stars. There are such exoplanets which orbit only one of such stars. Yes, there are many discoveries around such systems also, and you can find something called as binary stars with exoplanets catalog. There is a very good catalog available online where you can see so many binary star systems detected with exoplanets.
Okay. Sir, I have a few more questions. Sir,
Yes, ma'am.
can the binary systems be like we have two type of stars, that is the absorption and the emission stars. So
Yes, yes, true.
they are the same category of stars like absorption are binaries, or they can be in different format also, like absorption and emission star can be a binary also.
Yeah. Actually, whenever you take the spectrum from the star, I mean, let's say spectral from the binary system. So whenever here I have put an example for you. So most of the time, what do we do is whenever we get the spectrum from a star, so whenever you observe absorption lines like this, in this case, we try to determine something called as equivalent widths. Okay. So depending on the equivalent weights or like the fillage or like the filling of these spectral lines, we try to understand what exactly is the nature of that particular binary star. Yes, there could be emission lines also. But during my research work or like in my studies, I have never found so many like or like say considerable emission lines. Whatever the absorption lines I have detected or like I have found, so they helped me to understand the nature of the binary system. Okay, so uh, whatever the data I have collected and I have studied, most of the time I have found absorption profiles only significantly, strongly filled in absorption profiles only. But there are some systems where you can find emission lines also, strong emission lines also. But each of these lines have a particular meaning, and each of them are associated with something related to the activity of the system, like I have mentioned here. So this particular image, this particular graph shows you like what lines can you expect in each of these regions. Okay, like if it is photosphere, what lines you can expect. If it is like chromosphere, what lines you can expect. So anyway, these are absorption lines only. Sometimes they are filled in absorption lines. But I did not find any emission lines during my research work. I have never explored those also anyways. Yeah.
Okay. So one more question. So can we look at the binaries using the telescope, as you said? Can we see?
Visual binaries, yes.
Yeah, the visual binaries. So can you name some so that we can? I have a telescope, so I can just roam around in the
Um,
sky.
Yeah, got it, ma'am. There are actually so many good examples for visual binary star system. I don't know which telescope you have, ma'am.
So I have an 8-inch telescope,
Acha,
celestial.
oh, a Celestron 8-inch. Um, so 8-inch means I think you can observe till 10th or 12th magnitude. If you are living, just let me know if you live in a city or like say countryside.
So I am in a city, but very nearby to the countryside. My Doctoral sky is around 5, but
Okay.
just 10 or 12 kilometers, it will be around 3.
Yeah, understood, ma'am. Got it. So, as you said, you have an 8-inch telescope. So, generally, 8-inch telescopes are they have like very I mean, they're like very conditioned. But I can give you some examples. Let's take example of Mizar and Alkar. You know
Yeah,
Arundhati and Vasishtha, right? So they are
yeah,
very famous. Yeah, they are very famous pair. Mizar itself is a binary system. You can clearly see its I mean, its other components with an 8-inch telescope. You can try it. So Mizar and Alcor, they are part of Big Dipper. Then you
okay,
have other example, Castor. You know Gemini constellation, right?
yeah,
Yeah. So you can look at Castor. Castor can also be resolved with hopefully resolved with an 8-inch telescope from your place.
okay,
Then you have Sirius also, I think you can give it a try, man. Sirius also you can give it a try. And then you have something called as Alberio, which is part of Cygnus constellation.
yeah,
Hopefully you should be able to resolve it because it is a very well-known colorful binary. It has contrasting colors. You have blue and orange colors. So if you make use of your 8-inch telescope, go to countryside, and if you look at look for Beta Cygni, which is Alberio, part of Cygnus constellation, hopefully you should be able to find it. So these are all examples for visual binaries only.
right. And so, like, I am a citizen scientist, so I have been doing some projects on planet hunting, like the planet
Good,
hunter
ma'am.
test. We
Yeah,
get
yeah,
the
yeah.
data from the test telescope, and
Yes, yes,
we
yes,
try
yes.
to analyze the light curves. So,
Wow.
does that citizen science project really help the scientists to do their scientific work, or it's just for our engagement or satisfaction?
It's a good question, ma'am. Generally, what happens is we have now very powerful pipelines. So most of these pipelines will detect almost all the planets, whatever possible. But whatever the data you get for Zooniverse or eclipsing binary tools or like say planet hunting or galaxy zoo and all, so those can be done with your visual inspection. Most of the time, these are through your visual inspection. where you have comparison, where you try to basically like you can visually check it and you will justify whether this can be a planetary candidate or not. So this will sometimes help scientists. It's not just like they have given you some data which is not useful. It's not at all true. There are many citizen scientists who have discovered um, many like planet candidates also. So planet hunter is like one of such examples. So yes, visually, uh, people will look into each of the light. I'm just giving you one example. Each of the light curves where they will put on voting, like whether it belongs to expected candidate or not, and all. Yes. So depending on that, there are some very beautiful discoveries quoted by some citizen scientists. So it will help the scientific community a lot. So this will add on to the whatever the discoveries which are there, so that it will become a potential candidate for next observations.
Okay, okay, okay. So, can you suggest some books on spectroscopy?
Spectroscopy, yeah, ma'am, I can do that. You want?
In a very layman term, because I am not a
Okay.
physics student. I am just a passionate astronomer. That's it.
Okay, ma'am. Then you can like take my email ID and you can just let me know. I will share you some resources which give you like a very basic introduction to spectroscopy so that over a period of time you can explore it in detail.
Yeah, yeah.
Yeah,
And
I will keep the last slide. So you can just make a note of my email ID, or you can scan my LinkedIn also. You can ping me on LinkedIn if possible. So I will share you some basic material so that you can explore it beyond that.
sure, sir. Thank you so much.
Yeah.
And sir, one last question. So when the two binaries combine, as you
Yes, yeah,
said, that
much.
it takes millions of years, lakhs of years to when they really combine with each other. When they
Yes.
combine, we know that it is a supernova explosion kind of a thing. And
Yeah, whenever they are compact and yeah, yes, ma'am.
yeah,
It depends. Yeah.
sir, do we have some kind of definitely there is an energy release, and is that energy release is some kind of GRB or something else?
Huh.
Is it the
Gen
gamma ray burst or something else?
So generally, ma'am, what happens is actually we never witnessed exactly the binary merges till now, but there are
Okay,
some potential candidates. There are some targeted and potential candidates which may undergo, okay, which
okay,
may undergo like merging where they become blue stragglers. That is one possibility. The other possibility is like you have questioned, like what happens if two compact binary star system, like say one compact and the other normal star, like they undergo supernova. So generally what happens is in order to undergo a supernova, especially type 1a supernova, where you have one red giant and one white dwarf, where this white dwarf continuously accumulates um, mass from the other companion or like the companion star. So over a period of time, they either it gets matter and gets it accreted, or it will merge with the other white dwarf. Okay, once it approaches a critical mass limit, we generally call it as Chandrasekhar mass limit. I think
yeah,
you know
yeah,
it, 1.43
yeah,
or 1.44. So
yeah.
once it reaches that, it will exceed its limit. So it gets ignited. Then it undergoes a thermonuclear explosion, which is like a huge explosion. It will destroy the star. Okay. And now you have asked me like earlier, yeah, someone has asked me like how these are like standard candles. Yeah, it yes, type if it is type 1A supernova. So generally these type 1A supernova are known for their strong silicon absorption lines. Okay. So they
Okay,
are extremely luminous, and whenever they happen, so their brightness is so much that they are sometimes brighter than the galaxies itself.
oh,
Okay, so because of that peak consistent brightness, okay, they are considered to be like standard candles. Yeah, someone has asked me the question why they consider them to be standard candidates. The reason is this: because of their peak, very huge brightness, and that too, the brightness will stay for longer duration of time. So they help us like standard candles or something. Now coming to gamma ray bursts. So I don't think with the, I mean, whatever the knowledge I have, so gamma ray bursts. I don't think that it has nothing to do with this particular
Okay.
this type 1A supernovae, because gamma ray bursts are a bit different, I guess, because generally whenever a massive star, okay, whenever they undergo a supernova or hypernova explosions, where they ultimately die as a black hole, there you can expect gamma ray bursts. And these gamma ray or GRBs, these GRBs will hardly, I think, will stay for few seconds, I guess. And then you have neutron-neutron star merging or neutron binary star merging. In such a case, you can expect GRBs again. Not, not in the case of type 1A supernova, but in the
Okay.
case of neutron-neutron star merger, or like say neutron by a neutron black hole merger,
Yeah.
where they produce black holes, right? So in such a
Yeah.
case, you can expect GRBs. But anyways, these GRBs can be like say very like they happen like very for smaller duration, hardly for few seconds.
Okay. 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 Right. So thank you so
Yeah, ma'am.
much. And
No, it's okay, ma'am.
one last question. Sir, can we buy a spectroscope as an individual, not as an organization, but as an individual?
Yes, ma'am. Actually, yes, you can do that. There are some very basic, I mean, for your basic research, you can do that. There are some instruments you can buy. I mean, I can share you the websites where you can, let me give SBIG. Search for SBIG spectroscopes, where you can get a small spectroscope where you can do your basic research. I mean to say you can conduct that research making use of your 8-inch telescope with that spectroscope, observing bright stars, whatever
Right.
bright stars which are available.
I asked you this because I have been observing sun from past 3 years regularly on a daily basis. So I
Yeah,
just
ma'am.
wanted to do some kind of spectroscopy work.
And there are some people who generally build their own spectroscopes also.
Yeah,
If you, yeah, if you don't want to do that, you can go with SBIG instruments where you can get a CCD and a spectrograph also, where you can make use of it and do significant work. Or you
right.
can build your own, but building it is like a more of
Yeah,
um, technical thing, and you have to collaborate with some good laboratory where like you get some support where you can work on it. But if you have some funding, you can go for SBIG instruments.
right, sir. Right, sir.
Yeah,
Thank
ma'am.
you so much for the insightful session. It was
Oh,
really
thank you.
uh, so much of learning for us. Thank you so much.
Oh, thank you so much. Thank you for your positive words. Yeah.
Thank you, sir.
Thank you, ma'am. Thank you. We share your gratitude with sir. I think this is about the end of the session. We will take one last question. I think Yashwant has been raising his hand for a long time. We will take one last question and we'll then give our thanks and end the session. Yashwant, you may open your mic and ask the question.
Uh, yes, sir, I'm Ishwant here. My
Yeah,
question
yes.
is that if there's a planet orbiting a binary star system,
Mhm.
mainly where the binary star system, as they're about to combine, so will it be
Mhm.
orbit around the binary star system will be defined or not be defined, or like stable or not stable?
You mean to say that the exoplanet will affect the center of mass of the system?
Yeah,
You see, again, it depends. See, we should not forget that if you take example of Sun and Jupiter, Jupiter is pretty small. We know that, but still, the center of mass of Sun and Jupiter is not exactly at the center of the Sun like any other planet. It is bit off shifted. Similarly, if you take binary systems, depending on the mass of the third body and where it is exactly, accordingly, the center of mass of the system is defined. If the central pair or the binary system has pretty close binaries, and if they are very massive, in such a case, the center of mass will be between them. Okay. If the exoplanet or if the third body is pretty massive and it is like not that far. In such a case, yes. So it completely depends on the mass distribution of the system. Accordingly, your center of mass will be there, and you have asked me one more question, like if they combine or if they merge together, what happens? See, we should not forget that center of mass is all about mass distribution, right? If two systems, if two stars are massive, and if already there is a defined center of mass, if they come closer, also still there will be center of mass there only. Center of mass won't shift because already they are there on either side. So whenever they combine, also the center of mass will be at the center of the system. But if the third body is like extremely massive, if the third body is like tidally affecting the central system, in such a case, yes, there can be a possible effect in the location of the center of mass.
Okay. Like, and last question, like the cosmic the CMS of coronal mass ejection from our own sun, can the CMS affect our observations of other stars?
Acha, you mean to say like whatever the coronal mass ejections, um, whatever like are there, like do they affect the observations of other stars? In what sense? Like I didn't get you. See, generally, if you look at the night sky, okay, we are exactly looking it from the darker side, right? So whatever the space telescopes we have, they are generally faced away from the sun. So coronal mass ejections are pretty massive ones. So huge amount of mass is thrown now. One CME is enough to kill us also. We should not forget that. So as I understood from your question, you are asking that does CMEs affect our observations of other stars? So most of these space telescopes are faced away from the sun towards the night sky. They orbit in such a manner only. So they continuously monitor the night sky, which is off the sun, other side of the, I mean, like other than the sun side. So accordingly, they move also. We should not forget that. Accordingly, you have your sectors. I mean, your sky is split into different sectors. Accordingly, they will observe that particular sector. So if CME is so strong that it is expanding till so many millions and billions of kilometers, that too very bright. Yes, in such a case, obviously it will affect your detector also, no? But 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 if it is not that strong, if it is not expanding beyond some millions of kilometers, then no.
Okay, thank you, sir.
Yeah.
All right. All right. I think we've got a couple more questions in the chat.
Yes.
Yeah, it's some Babita has asked if the sun were a binary system, what impact would it have on our solar system?
Okay. Yeah. This question generally, yeah, it's a very interesting question. So if sun would have been part of a binary system, there are two possibilities. If it is a part of a wide binary system, means the other component is pretty far from us, then we will be orbiting the sun more or less like this. But if it is a closed binary system, if sun is part of a closed binary system orbiting around each other, around the common center of mass, then there is a very less chance that Earth or like any other planets might have formed like this. They might have been like thrown off very farther from the system. We should not forget that. So there are some exoplanets which orbit around both the binaries also called as circumbinary planets, but it would have been a different thing. So you can see some where science fiction movies may there will be some planets where there are two stars in the sky. Yes, there is a possibility. There are some planets, exoplanets around such around the binary systems also. But if sun is a part of a binary system, means it depends what type of binary system it is, whether it is a wide binary system or if it is a closed binary system. Accordingly, our life depends. I mean to say our existence depends.
Thanks. One last doubt somebody has. In a binary star system, how does the presence of two stars affect the formation and stability of planets? And is it possible for planets to exist in stable orbits around both stars or just one of them?
Yeah, this is very important and very pretty interesting question. So, see, remember, whenever, as I just told you, if it depends on like whether they are wide binary stars or like closed binary stars. If, let's say if they are very close binary stars, yes, there are chances of exoplanets existing around closed binaries also. But the orbits are pretty farther. Um, I think according to some models, the exoplanets are way too far. They are called as wider exoplanets. I mean, the orbital distance will be more than 100 AU to have a stable orbit around the binary system. So you can understand we are at one astronomical unit. Just assume an exoplanet around a binary system at 100 AU. 100 AU is like very pretty far distance, right? And there are some exoplanets around one star also when there are two stars in a system which are very well separated. Yes, there are such systems also. So yes, they can have stable orbits, they can have unstable orbits also, depending on how they form and how they are evolving accordingly. Yes. So there are some exoplanets which have very good stable orbits, but they are very farther from the central system.
Great. All right. Thank you so much, sir, for coming here to speak. I think we'll mark our conclusions of asking questions here. Thank you so much
Oh,
again
yes.
for coming here. Such great questions, such great topics to talk about. We'll mark
Yeah.
our conclusions here. I think we should end the session since we had a time constraint. We have gone much overflown it much more. Uh, we will we are extremely grateful to you for coming here, sir, and answering so many questions for so
No,
many
no,
people.
no.
Yeah, thank you
I
so
don't know
much.
whether I have answered all of those questions or not because some questions are like out of my research area, so I'm not explored much some concepts. But yeah, I have. I hope I have answered like at least like close to their expectations. Yeah. Thank you
Yeah,
so much for having me today. I should be very thankful. We have very good audience. They're like very interactive.
yeah,
Thank
yeah.
you, sir.
We have a
Thank you
great
so much for answering all our questions. Really,
No, no,
you
no.
have been
Thank
so
you.
patient in answering such little and so what we say the basic questions like what I asked. Matlab, they were really petty questions
No,
for you.
not at all. Not at all, actually. Any question is a question, actually. As an observational astronomer, we should have such a patience.
Yeah.
So observations teach you a lot, actually. We stand for hours of time for just teaching students and having observations. So we have that much patience. We should have actually. Astronomers must have patience. The time scales are pretty long, actually.
Yeah.
Right. So thank
Although
you
they,
so much.
yeah,
Yeah.
although ma'am
Thank you
thought
so
they were
much, sir.
but very important
Thank
questions,
you all. Thank you all.
we really enjoyed them all.
Thank
We'll
you
mark
so
our
much.
end of the sessions. We'll take maybe a couple more minutes to call upon my friend. We'll tell you a few things about propagation, what we do, and then we will end the session for everybody. And you all can. Most of the people are from India, some are them from Russia. So you can mark your ends of the day. All right. I'll call upon my friend Jitu here. We'll tell you a few things about propagation and we'll mark the conclusions. All right. Jitu, you may speak. Yes,
Yes, you are.
yes, audible.
Yeah, just a second.
I will take a couple of pictures to mark your sessions. Yeah.
Actually, we have a power cut here, so I was unable to switch on my camera for the because I have to keep it on hotspot. So
Uh,
no, no, not an issue. I can answer them. Yeah, I'm happy to do that.
yes. Yeah. Yeah. All right. People have turned on the cameras. A few people have not because they might be in obscene positions, but don't worry. We'll take pictures. We'll take the pictures. Yeah. Let me take another one. All right. All right. We have our
Yeah,
pictures,
thank
sir.
you.
Thank you, everybody. We'll mark our conclusions. Thank you so much, sir, for coming here. We are extremely grateful to you. Thank you so much to people who have come and asked some great questions. Thank you, Amoli ma'am. We'll mark our ends here. See you next Sunday. We'll
Yeah.
have much more. We'll have much more events. We have Space Week next week as well, so we'll start with that as well. I'll end the call. Thank you, everybody.
Yeah.
Thank you, everybody,
Have
for
a
coming.
great night. Yeah, good night.
Yeah.
Take care. Bye.
Have a good night. Have a good night, everybody. Thank you, Jitu. Thank you, Amulya ma'am. I'll stop the recording and end the session.
Thank you so much.
Thank you.